Hello everyone, my name's Iman. Welcome back to my YouTube channel. Today we're going to be discussing oxidation-reduction reactions, and in this chapter we will cover the following topics. First, we're going to define oxidation and reduction. Second, we're going to go over the rules for assigning oxidation numbers. Third, we will explore disproportionation reactions. This is a unique class of redox reactions. And finally, we're going to learn how to balance oxidation-reduction reactions. With that introduction, let's go ahead and get started. Reactions that involve the transfer of electrons between chemical species are classified as oxidation-reduction reactions, also known as redox reactions. At their core, these reactions embody the principle of conservation of charge, which states that electrical charge cannot be created or destroyed. This principle ensures that whenever one species loses electrons, this is a process known as oxidation, another species must simultaneously gain those electrons, and this is a process known as reduction. So to put it simply, oxidation is the loss of electrons, and reduction is the gain of electrons. These two processes are interconnected, again, because the electrons lost by one substance must be gained by another. A helpful way to remember this is through the mnemonic Leo the lion goes grr. Leo stands for losing electrons is oxidation, and grr stands for gaining electrons is reduction. Alternatively, you might find oil rig a bit more helpful. Oil stands for oxidation is loss, and rig stands for reduction is gain. To illustrate this, let's consider the reaction between magnesium and hydrochloric acid. The balanced equation for this reaction has a coefficient of 1 in front of magnesium, a coefficient of 2 in front of hydrochloric acid, and a coefficient of 1 in front of both magnesium chloride and hydrogen gas. In this reaction, magnesium undergoes oxidation because it loses 2 electrons. At the same time, hydrogen ions from hydrochloric acid gain electrons and are reduced. You might be wondering, how can we identify which species are oxidized and which species are reduced? The key lies in oxidation numbers, which we're going to cover shortly. For now, I want to introduce 2 important terms related to this process. Magnesium acts as the reducing agent because it donates electrons and undergoes oxidation. At the same time, hydrogen ions act as the oxidizing agent because they accept electrons and undergo reduction. But what exactly do these terms mean? Let's formally define oxidizing and reducing agents. An oxidizing agent is a chemical species that gains electrons during a chemical reaction. By accepting electrons, it causes another species to lose electrons, which is a process known as oxidation. In other words, an oxidizing agent is reduced while oxidizing another substance. Oxidizing agents are typically elements or compounds with a strong tendency to attract electrons due to their high electronegativity or electron affinity. Common examples include oxygen, which can form strong bonds by accepting electrons, and halogens like chlorine and fluorine, which are highly electronegative. A reducing agent, on the other hand, is a chemical species that donates electrons in a reaction. By losing electrons, it causes another species to gain electrons, and this is a process known as reduction. In this case, the reducing agent itself is oxidized while reducing another substance. Reducing agents are often metals which have loosely held electrons that can be easily donated, or compounds containing hydride ions which readily release electrons. So for instance, sodium, which is a metal, and sodium borohydride, which is a hydride compound, are typical reducing agents. We can visualize this interplay using the diagram you see here. So compound A, when oxidized, loses electrons. These electrons are transferred to compound B, which is reduced. So as a result, compound A acts as the reducing agent, and compound B acts as the oxidizing agent. So to simplify this, the chemical species that is oxidized is the reducing agent, and the chemical species that is reduced is the oxidizing agent. Now that we understand what redox reactions are and how electrons are transferred, it's time to discuss oxidation numbers. An oxidation number is a bookkeeping tool that helps track the electrons assigned to each atom in a compound or molecule. It simplifies complex bonding by treating all bonds as though they're purely ionic, and it assigns the electrons in each bond to the more electronegative atom. This method allows us to identify which atoms are oxidized and which are reduced during a chemical reaction. To assign oxidation numbers accurately, we follow a set of rules. So the first thing we're going to do is we're going to review these rules to build a strong foundation. Then on the next page, we're going to refer to the periodic table and use it to identify patterns and general trends that will make applying these rules easier. With that, let's start with rule number 1. Rule number 1 says the oxidation number of any atom in its elemental form is always 0. So for example, oxygen gas, hydrogen gas, and elemental sulfur are going to have oxidation numbers of 0 because they are all in their elemental form. The second rule states that the oxidation number of a monatomic ion equals its ionic charge. So for example, if we're talking about a sodium ion, it's going to have an oxidation number of +1 because its ionic charge is +1. Same goes for chloride ion. It's going to have an oxidation number of -1 because its ionic charge is -1. The third rule states that in binary compounds, the element with the greater electronegativity is assigned a negative oxidation state equal to the charge it would have as a monatomic ion. And the fourth rule says the sum of the oxidation states of every atom equals the overall charge of the substance. To fully understand these last two rules, we need to go over some general trends in oxidation numbers. And to do that, we're going to look at the periodic table. To start, let's look at alkali metals. Alkali metals are elements in group 1, and they always have an oxidation number of +1 in their compounds. So if we were to look at sodium in sodium chloride, it would have an oxidation number of +1. Similarly, alkaline earth metals, which are elements in group 2, they always have an oxidation number of +2 in their compounds. So if we were to look at magnesium In magnesium chloride, it would have an oxidation number of +2. Halogens are elements in group 17. They generally have an oxidation number of -1. However, if a halogen is bonded to a more electronegative element, its oxidation number can actually change. So for example, in hydrochloric acid, chlorine is the most electronegative element. So it's going to have its typical oxidation number of -1. But if we were to look at hypochlorous acid, oxygen here is the most electronegative element. So chlorine is not going to have its typical oxidation number of -1. Hydrogen usually has an oxidation number of +1 when it's bonded to nonmetals. The rules change when hydrogen is bonded to metals. When hydrogen is bonded to metals in metal hydrides, it actually has an oxidation number of -1. A good example is sodium hydride. Hydrogen in sodium hydride has an oxidation number of -1. The last element we want to talk about now is oxygen. Oxygen typically has an oxidation number of -2. So if we were looking at carbon dioxide, oxygen here has an oxidation number of -2. But there are two exceptions that we need to commit to memory. The first exception is peroxides. In peroxides like hydrogen peroxide, oxygen has an oxidation number of -1 because of the oxygen-oxygen bond that exists. Another exception is oxygen difluoride. Here, oxygen has an oxidation number of +2 because fluorine is more electronegative. With this in mind, let's revisit rule number 3 and rule number 4. Rule number 3 says, in binary compounds, the element with the greater electronegativity is assigned a negative oxidation state equal to the charge it would have as a monatomic ion. Let's look at oxygen difluoride. Here, fluorine is more electronegative. Therefore, it's assigned an oxidation number equal to the charge it would have as a monatomic ion. For fluorine, which is a halogen, it would have a charge of -1, which means its assigned oxidation number is -1. Now, rule number 4 is going to help us assign the oxidation number of oxygen in this case. Rule number 4 says, the sum of the oxidation states of every atom equals the overall charge of the substance. For neutral compounds, the sum of all oxidation numbers equals 0. We've assigned fluorine here an oxidation number of -1, and there's a total of 2 fluorines. So we have a total of -2. Oxygen difluoride is a neutral compound, so we need the sum of the oxidation numbers to equal 0. That means that oxygen has to have an oxidation number of +2 in this case. +2 minus 2 equals 0, which is exactly what we want for a neutral compound. Now, what about for polyatomic ions? For polyatomic ions, the sum of the oxidation numbers equals the ion's charge. So if we were to look at the sulfate ion, SO4 2-, the sum of the oxidation numbers here has to equal the ion's charge, which is 2-. Let's work through this. Oxygen has an oxidation number of -2, and there's a total of 4 oxygen atoms. So we have -8. We need the sum of the oxidation number of sulfur and -8 to be equal to 2-. This means that Sulfur has an oxidation number of plus 6. Plus 6 minus 8 gives us minus 2, and we know we did this correctly because the sum of the oxidation numbers equals the ion's charge. With this information, let's tackle a practice problem. This problem says, assign an oxidation state to each element in the following compounds. The first two elements that we have here is oxygen gas and solid iron. To figure this out, we need to rely on rule number 1. Rule number 1 says that the oxidation state of an element in its neutral elemental form is 0. That is the case for both oxygen gas and solid iron. They're both in their elemental form, so their oxidation numbers are both 0. Then we have magnesium oxide here. Now, to solve magnesium oxide, we need to recall rule number 2. Rule number 2 says the oxidation state of a monatomic ion is the same as its ionic charge. Magnesium oxide is an ionic compound. It consists of both the magnesium 2 plus cation and the oxygen 2 minus anion. Therefore, the oxidation state of magnesium is plus 2, and the oxidation state of oxygen is minus 2. Let's do a bonus one. Let's do Fe2O3. To solve this, we need to recall rule number 3, which states in binary compounds, the element with the greater electronegativity is assigned a negative oxidation state equal to the charge it would have if it were a monatomic ion. Here, oxygen is more electronegative than iron, so it's going to be assigned an oxidation state of minus 2 because its most common ionic form is O2 minus. Then to figure out the oxidation number of iron, we have to rely on rule number 4. Rule number 4 says the sum of the oxidation states of every atom equals the overall charge of the substance. This is a neutral compound. So the sum of the negative oxidation states has to be equal to the sum of the positive oxidation states. Here we know that the oxidation number of oxygen is minus 2, and we have 3 oxygens. So we have a total of minus 6. For iron, we have 2 iron atoms. They're going to have an oxidation state of positive 3, and there's 2 of them, and that gets us a total of plus 6. This is good. Plus 6 minus 6 equals 0, which is exactly what we want for a neutral compound. So again, the sum of the negative oxidation states here is 3 times minus 2, which gives us minus 6. In order for this compound to be neutral, the sum of the positive oxidation states must be positive 6. There are 2 irons, so each one has an oxidation state of plus 3. And with that, we've solved this example problem. And now we want to revisit this chemical equation and explain why magnesium gets oxidized and the hydrogen ions in hydrochloric acid gets reduced. To start, we want to assign everything an oxidation number. Let's begin with magnesium on the reactant side. Magnesium here is in its elemental form, so its oxidation number is 0 according to rule number 1. Now on the product side, magnesium appears as part of magnesium chloride. In magnesium chloride, chlorine is the most electronegative element, so it's going to have its typical oxidation number of minus 1. Here there are 2 chlorine atoms, so there is a total negative charge of minus 2. To satisfy rule number 4, which states that the sum of oxidation numbers equals the overall charge of the compound, magnesium must have an oxidation number of +2 to balance the -2 from chlorine. So now we're looking at magnesium's oxidation number in the reactant side and in the product side. And we notice that the value increases. Magnesium's oxidation number increases from 0 to +2, meaning that it loses 2 electrons and it is oxidized. Now let's focus on hydrogen in hydrochloric acid. The hydrogen in hydrochloric acid has an oxidation number of +1. This is just following rule number 3. And we also covered that hydrogen typically has +1 when it's bonded to nonmetals. Now on the product side, hydrogen appears in its elemental form as hydrogen gas. So its oxidation number is 0 here following rule 1. We notice hydrogen goes from +1 to 0. Hydrogen decreases. The oxidation number for hydrogen decreases from +1 to 0, meaning that hydrogen gains electrons and is therefore reduced. So now we understand why we said magnesium is oxidized and the hydrogen ions in hydrochloric acid is reduced. Now you might be wondering about chlorine. So let's try to figure this out. Chlorine in hydrochloric acid has an oxidation number of -1, and the chlorine in magnesium chloride also has an oxidation number of -1. So chlorine here is neither oxidized nor reduced because it doesn't change during the reaction, and actually it really just acts as a spectator ion in this redox process. So now we know by carefully applying the oxidation number rules, we can figure out which chemical species is oxidized and which chemical species is reduced. And with that, we can move into our next topic, which is disproportionation reactions. We're going to cover this actually in the next video. So for now, that's all I have for you. I hope that this was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.